can everyone see these slides?
Yep.
All right, thank you very much. And I do appreciate, I just saw feedback from one of the participants. I do appreciate feedback at any time. What I'm actually doing right now is I'm opening up the chat window and I'm making sure that I have the chat window open beside me. And I'm going to open up the participant window so that if anyone has a question or a comment, interact with me. I love that. I don't want this just to be one way. Okay, so what we'll do is we'll talk about tree-based energy machine learning. It's going to be fun. We'll talk about a relatively simple form of machine learning, but you'll see it can build into a very powerful method, specifically random forests that can be used in cutting edge problems. It can be competitive with the most advanced forms of machine learning. All right, so what are we going to do? What's the goal? A little bit of introductions, machine learning basics. You know, we have to strip out some of the details. We can't tell you everything. We can't deal with all of the details in an hour and teach all of this, but we can definitely do a fast start, sprint to build some models. Also, if we had more time, we would all spend time building models together. There would be fingers to keys. Everybody would have a chance to build models and iterate. Instead, I will just show workflows and talk about it, but I will allow for inputs, so you can jump in and let me know if you have a suggestion as we do that. Now, we do need some context. We can't jump straight to tree-based machine learning. We will have to cover some machine learning basics. There's a lot more we could talk about for sure. Now, if you've never met me in person, you don't know how to pronounce my name, don't be uncomfortable. Just say it like Pyrcz. If you do that, I'll give you an A. That'll be like the expectation or the bar as far as pronouncing my name. And I have practical experience. I worked in the field for many years in the area of subsurface modeling, geostatistics, data analytics, and statistical modeling. And so what I teach is what I've done, and I know exactly how we can use it to add value. Our attitude is teach something in a morning that this afternoon you could use to add value in your organization. And we think that's a great idea. And what Kunal had mentioned previously is we've seen it. We've worked directly with mentored professionals and seen them actually be able to make major differences in the impact they have in their organization. If you're interested in what I do and you want to learn more about it too, besides Datum, follow me on Twitter, check out my YouTube channel, my GitHub, and so forth. I'm the geostats guy elsewhere. I also constantly collaborate with industry, and I hope it's okay. I'll throw in a little plug here. Like every professor, I have a consortium. And so you can find out about the direct consortium. I work with Dr. Foster, Dr. Torres Verdeen, and Dr. Van Oort within the University of Texas at Austin. And I have a group of students. Anybody has internships next summer, go ahead, contact me. I have great students in this area. Okay, goals of this lecture. Let's define some terms, introduce some concepts. That way, when we build machines, we can relate them, we can communicate, we can make choices. Okay, so let's go ahead. Digital transformation. Everybody is facing this right now. Every single company I visit, they're talking about it. They're working on it. Every company is trying to add value with new technologies. What's interesting, if you look at the Deloitte study back a year ago, they looked at the readiness of different sectors of our economy. And what they found was that energy was somewhere near the middle. We weren't at the trailing edge with life sciences, and we were not right there with tech, media, and telecom, but we were somewhere in the middle, and there was variable levels of adoption of new digital technologies. Now, I have biases, and I'll be honest about them. I should declare them. I think there's definitely opportunities to do more with data. I commonly tell people that my Chevron P10, my low case, would be we end up respecting our data and doing more with our data for sure. Now, there are opportunities to teach data analytics and statistical machine learning methods to engineers and geoscientists, and we know that. We've taught hundreds of them, and they've quickly learned, quickly adopted. They're ready to learn. We think that there's great connections. In fact, geoscience and engineering knowledge and expertise remains core to our business, though. We don't see the world just going to purely data-driven. We always see a hybrid. Now, let me just make a couple of comments about machine learning, and then we can dive into tree-based methods. Now, like many people, when I think about a topic, I Google search it and I find Wikipedia, like many of us do. And if you look at the definition in Wikipedia for machine learning, this is what you'll see right up front. is the study of algorithms and mathematical models. It's not just one model, it's an entire toolkit of methodologies that are used to progressively improve their performance on a specific task. Okay, a toolkit of learning methods. They learn based on build mathematical models of sample data known as training data. Okay, they're learning from training data in order to make predictions or decisions without being explicitly programmed to perform the task. That's important. These are methods that are general. We should be able to use them in one application, another application. They should be flexible enough to learn from the data. Now, a lot of people stop there, but it's very important to continue reading in the article, of course, get the fine print. Where it is infeasible to develop an algorithm of specific instructions for performing the task. In other words, these methods are not a panacea solution. In fact, if you understand the fundamental engineering and geosciences and you can solve the problem using that, you will have greater accuracy. There is a role in speeding up, streamlining, instantaneous feedback, and so forth. There's many good applications for machine learning, but we do not let go of the fact that the geoscience and engineering knowledge is critical. Let's talk a little bit about machine learning for prediction. Every time I say machine learning to debaffle this, just remember this equation right here. That's fundamentally what machine learning is all about. You have a function that takes a set of inputs. Now, back in the good old days, we called these independent variables. Now we call them predictor features, features for variables, and predictors instead of independent. Okay, so we got our inputs, our predictor features, and we've got our output, which is going to be the response features. And that used to be called dependent variables or variable. Now, machine learning is all about building that model F to be able to move from the inputs, the predictor features, to the output, the response feature or features. And so it's all about getting that function to be able to move through or translate. Now, we'll have two purposes when we do this, inferential and prediction. Today, we're going to focus on prediction. We're not going to talk about inferential machine learning. Estimating that function, f hat, represents an estimate of the natural system. The natural system, there is a real f. There is a way to go from the inputs to the outputs, but our goal is to estimate that function, the natural system, for the purpose of predicting y hat, the very best, most accurate estimates of the response feature or features. Now, so our model looks like this. We have an estimate of f to get an estimate of y. That's prediction, and that's the mode we're going to work in. Now, when you're doing prediction, there are two different types of models. We could break up prediction models into parametric and non-parametric models. This is very important. Our tree-based methods will be non-parametric. Just spoiler alert right there. For a parametric model, we make an assumption about the functional form or shape for the natural system. Now, we gain a lot. We gain simplicity and the advantage of only having a few parameters to work with. These are truly compact models. For example, here's a linear model right here. Super simple. Literally, we only have a constant parameter, and then for every input or predictor feature, we have one coefficient, a slope term. And that's it, just two. If we're working with an individual predictor feature, we only have two parameters. You can imagine linear regression. One of them will change the slope, the B1, and the B0 will move it up and down. Not a big deal. Now, there's never free lunch. The fact that we have this simple model with only a few parameters, now we have a risk that our f hat, our estimate of the natural system, is just wrong. It's quite different than the real natural system, and then we get a very poor model indeed. Non-parametric models are different. We make no assumption a priori about the functional form, the shape of the natural system. In fact, they're much more flexible than the parametric methods in that they can learn the shape of the natural system. Now, of course, there's less risk that our f hat is a poor estimate of the natural system, because whereas with the linear regression model, we were stuck with that linear model, here we can learn the form from the data. But there's always a trade-off. Typically, we need a lot more data for an accurate estimate of f. what I like to tell my students is non-parametric models are actually parameter rich. And you're going to see that when we do tree-based models. There's actually quite a few parameters in these models. Now, if we look at a parametric model as shown here, I want to illustrate this idea that we could be totally wrong. Here is a phenomenon. It's depth versus a standardized porosity measure right here. And if you look at the data, you can see it has this type of cycling. Not uncommon in a stratigraphic setting. You could have these types of cycles at different scales for sure. And in this case, we can see the cost of using a linear regression model. It's just too simple to fit the data. Here's an example where we show a decision tree model, and you can see that we have this ability to learn the cycles, learn the shapes, but for every one of those levels, there in fact is a parameter. All of these thresholds and levels are parameters for the model. And so we have quite a few more parameters to work with. We've gone way beyond 2 parameters like linear regression. Now, I want to show you how we build a machine learning model in just one slide. And this is really important because we're going to show you actual models. I'm going to do this, and I want to make sure you have a roadmap. You understand why we're doing every step of the process. First of all, we're going to take the available data and we're going to split it into 2 sets, training and testing. Okay, so if you look at this data set right here, all of these are the data. We're back to a problem where we're working in depth, and we have permeability and millidarcies right here. All of our data, we split it into training data are the X's, the circles that are filled in are the testing data. Now what we're going to do is we're going to withhold, we're going to pull out that testing data and we're going to throw it away. You're not allowed to look at it. You can't even peek at it. Don't even think about it. Okay, you thought about it, don't. So you've got to just get rid of it. And I'll tell you, this is hard because often what will happen is that some of the ideas from the testing data will get into your model. We try not to do that. Okay, so we got rid of those circles. Now what we do is we're going to take our model and train the model parameters on the testing data, on the training data, on the training data. So we train the model parameters on the training data. We'll get the very best fit. So we're changing the parameters in our linear regression model to maximize the fit with the data. We could talk more about how we do that. We're being pretty brief right now. Then what we're going to do is we will change the level of complexity of the model and we'll repeat that process. We'll fit. This was a first order polynomial. This is a third order polynomial. And this is a fifth. This is a seventh. We keep increasing the complexity and we fit the very best model to the training data. Now what we're going to do next is we're going to check. Remember that testing data I told you not to look at and we threw it away? You should remember where you put it. We got to dig that up again. We're going to bring it and we're going to put it into the model and we'll make predictions at the testing data locations and we'll get the error. These are the distributions for the error right here. And you pick the model that does the best at the testing locations. Now in the chat window, if anyone wants to jump in, I would appreciate it. Well, what would be the result? Which model would you pick if you were picking the model that minimized the error at the training data locations? What do you think? What would happen? Anyone? Would I pick the first order, the third order, the fifth order, or the seventh order? Which one fits the training data best? Well, of course, what will happen, you bet. Hey, wow, this is a great response. Thank you very much. People jumping in there. Now, I think those who said the third order, you're thinking ahead, and I do appreciate that. You're thinking about testing data match, right? The seventh order, I agree with everyone, Christian and the others who have said that, where basically what will happen is to get the maximum fit with the data, we'll pick the model with the greatest complexity. It has the greatest flexibility to fit the data. But I don't know about the height of your monitor above the foundation in your home, but I'm pretty sure this model is punching a hole through your foundation right now. It is completely inaccurate at the testing data locations. Now, Johanna said something about overfit. I'm agreeing with you and I'm about to define that. Okay, so we're going to take the testing data that was withheld and we can check. The whole point is we're trying to simulate the real world use of the model. And we can't do that. We actually need data for which we know the answer to do that. That's why we're going to withhold some of the data to try to perform that step. Now, I've used these terms a couple of times, so I got to define them now. Model parameter. Those are fit during the training phase with the training data. Okay, so here we have the model. It's a third order polynomial, and we have B3, B2, B1, and the constant term, or B naught. Those are the model parameters. And we all know if you change those, you move the model up and down, you change the shape, and so forth. Model hyperparameters are totally different. They constrain the level of complexity of the model. So if you're ever confused, ask yourself, does this thing change the complexity of the model? If it does, it's a hyperparameter, or flexibility is another way to see it. The choice of first order, second order, or third order, those are the hyperparameters. These choices right here. Okay, I hope that clarifies. That's for a polynomial model. When we build our decision trees, we will have different hyperparameters to work with. Now, Johannes already mentioned overfit, and I totally dig that. I do appreciate that. Okay, what is overfit? If you look up the definition, it'll say something about fitting data noise, data idiosyncrasies. Actually, I just built a really cool interactive workflow to demonstrate the impact of noise on overfit. It's really cool stuff. Increased complexity will generally decrease the error with respect to the training data set, but may increase the error with regard to the testing data set. Okay, so here we have a model right here, perfectly fit. It's a decision tree, so complicated, we fit the data perfectly. We're in a situation where our training error is right here, 0 error in training, and we have the maximum complexity of model we could ever imagine. Now, what we'll find though is that while the training error is dropping, what will typically happen is the testing error will drop and then it'll start to rise up again. When you're in that region where the error is increasing in testing, remember the simulation of real world use of your model, but the training error is continuing to drop. That is the zone of overfit. That's what we're trying to avoid. We want to maximize the performance, minimize the error in the real world use of our model. And this would be a much more gentle model right here. All right, or a less flexible but better model. What's very interesting about this is often we find that the lower complexity models outperform the real complicated models, and that can even impact model choice. And we could talk about that in greater detail. Okay, let's go ahead and talk about decision trees, and then we'll go ahead and build some decision trees. I've got a slide deck right here introducing decision trees. We'll do this a little quicker than we would in the regular course because I want to play around with them. And then I want to talk a little bit about random forest, of course. This is an example of a decision tree right here. Not the most powerful methodology, but the basis for more powerful ensemble tree-based methods, okay? Let's talk about decision tree. Recall this function right here. Why? Because I'm talking about machine learning, and every time I say machine learning, we're all supposed to think about this function, okay? So we're all gonna think about that function together. Okay, we're predicting the response given the inputs, the predictor features. I will use those terms over and over again as we go. Predictor features, input, response feature, or features, output. We could work with continuous response feature or features or categorical. We will work with continuous, so we are in fact doing regression trees, random forest for regression. Why cover these methodologies? Not the most powerful or cutting edge, simple to understand, great introduction, and forms the basis of more powerful methods. And what I like to say is, if you want to learn about the forest, you must first comprehend the tree. Very cool, right? Okay, what's the fundamental idea here? We may have geoscientists on the phone. I expect we do. You know already, or even engineers, you know already about the issue of segmenting the subsurface. You know about segmentation and how it improves your predictions. You do FACES modeling, I bet. Well, it turns out the machine learning people were thinking the same way. They thought if we could take the predictor feature space, remember that term, the inputs, and in this case, I have just two of them so we can visualize it. We have predictor feature 1, predictor feature 2. Those are my inputs. Here's all of my training data. If I take that space and segment it, can I not make a prediction as the average of the data within each one of those regions? It's a discrete model from the standpoint that we would have constant estimates here, here, and here. And so there'll be step changes in our model. Not a big deal, but it should work pretty good. The fundamental idea is we got to segment the predictor feature space into mutually exclusive, exhaustive. Mutually exclusive, meaning that there's no overlap between the regions. Exhaustive, meaning there's no gaps. Okay, we need to make predictions everywhere across the range of possible predictor feature values, okay? Now, this is an example right here. It's one predictor feature just for ease of visualization, and I'm communicating that we're just segmenting region 1, 2, 3 through 4, and we are estimating with the average of the training data within every one of those regions. That's all we're going to do with a decision tree. Now, you might look at this problem and say, well, I can do some pretty awesome segmenting. In fact, if you look very carefully, this is porosity versus brittleness, a geomechanical property, a ratio, percentage. And we have the production. If you look carefully, these are dark colored dots, high production. This is gas production, MCFPDs. And then we have kind of a medium red and a brighter red. Okay, so you can see the color bar right here. If you drew these contours, you would get an awesome model. It would do very well. But can I convince you to make an abstraction? Instead of that, will you accept that? Instead of that, could you accept that? If you do, you will gain a huge amount of simplification. In fact, I can parameterize this model very, very easily. In fact, what you're going to find out, it's just a hierarchical segmentation. Segment here, segment here, segment here, segment here, and so forth. That is a decision tree. That's the whole fundamental idea. Okay. Now, how are we going to decide where to segment? How do we decide the goodness of our model? We're going to do what machine learning often does. We're going to come up with what we would call a norm, a measure that summarizes model performance. In this case, it's simply going to be the residual sum of squares. Many people use mean squared error. It's basically the same, but without doing the mean. And so we're just going to go ahead and sum the error, the true values of the training data, minus the estimates, the average within the region, squared, and we'll sum over the training data in each region, and then we'll go over all of the regions. That's all we're going to do. A very, very simple cost function that we're going to use here to describe model performance. Then what we're going to do is we're going to be greedy. I don't mind being greedy. In numerical methods, it's not too bad to be greedy. So we'll be greedy. We'll do recursive binary splitting. We'll start with all of the data in one region. There's one big region, and then we're going to go across all of the range of one feature, all of the range in the other feature, and we'll repeat for all features. And greedy, we're going to find the very best split that will minimize that error. That's what we're going to do. Now it's top down. I hope you can see that because we start with all the data in one region, and then we're going to split, 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 and we'll progressively split until we've reached the stopping criteria. Okay, so what does that look like? Let's do it once again with one predictor feature for perfect observability. We got porosity, production. I threw brittleness away. We took a break from brittleness. It's coming back, don't worry. And then what we do is we could move that split across the range of porosity values. And I hope you can see intuitively that this would not be a good split. Look at all of the error. That would be a lot of error. And I hope you can see this would not be a great split either. But if you look right here, we're getting to a better split. We're doing a better job. All right. Now, there's a question from Johannes right here, and I do appreciate the question. Jump in anytime, guys. This is interactive. Is producing segmentation in the tree model here similar to how we produce decision boundaries for SVM, support vector machines, right? Now, that's very interesting. We do have a full lecture we do on support vector machines. In general, I would say it's not quite the same. And this is what's very fundamental. A support vector machine is designed to only consider data close to the boundary. A decision tree does not. It considers all of the data. And that is the fundamental difference. In fact, what's very interesting, it makes support vector machines very powerful when data density is very variable or variable over the predictor feature space. While a decision tree will be very sensitive. Let me give you an example. If I put 1 million data right here, just in a tight little density, like a little dense circle right here, just data, of course, this overall result would be greatly influenced by that. While a decision tree would actually not be influenced by data that's outside of what we call the margin. It's fascinating. It's really interesting. Plus, there's a lot of details about a projection to a higher dimensional space with kernel trick and all that, which is really cool stuff. A very fun discussion. Thank you for bringing up. Yeah, Mustafa, I really do appreciate it. May use PCA first. And so this is what I would say, is when we teach machine learning, we talk about inferential methods like PCA and clustering and so forth, and we introduce them as perhaps essential feature reduction or dimensionality reduction approaches that can be used as pre-processing before we build our models. They can be very powerful, and I do appreciate that. You notice I'm cheating here. I'm using very, very few parameters just for visualization. Many of our problems have huge parameterization, or I should say huge number of features, high dimensionality, and with lots of risk for redundancy between the data, which actually really does cut into the model accuracy. It increases what we call model variance. We don't have time to talk about that right now, but really interesting. Thanks a lot, Mustafa and Johannes. I do appreciate you jumping in like that. Okay. You bet, my pleasure. Okay, so just to kind of cement this idea of the decision tree, we find the very best split. We're greedy, 14.4% porosity. Then we look across region 1, region 2, we find the very best next split, and you can see how we're growing an upside down tree. Okay, let's go back to our 2 predictor features. Feature 1, feature 2, we made our very best first split. We got our very first decision right here. This would be known as a stump tree. It's just one decision. That's no good. We got to grow something more like a crepe myrtle. We want something really complicated, right? Okay, so we find our very best next split right here. And notice how both of them are in porosity. This is interesting. This is important. And then we have a split on brittleness. Notice that the splits only go across a single region. That way it actually is a decision tree. Okay, we just travel down those branches. Okay, when do we stop? We could continue until every one of the training data are in their own regions. That would be truly an overfit tree, and I showed you an example of that. Typical approach is to apply a minimum training data in each region. I like that. As a statistics person, it tells me that I'm predicting with an average. I need enough data to calculate an average in every one of the regions. There's a variety of different methods that are used. Now, the typical way that we're going to do this is let me just go ahead, and I think now we can go ahead and jump into and build a tree, and then we'll demonstrate the idea of simplifying the tree. In fact, what I'll do right now is, instead of going through any more of this lecture, let's go ahead and go to code. Okay, so where do I have some code we can look at? Let me know if you all are having any difficulty visualizing or seeing this font. I'm going to zoom in a bit. Is that good? Can you all see this on your respective screens? Okay, let me know if you have any issues with visualizing this. Okay, so we have an example right here. Thank you very much, Mohammed. Thank you very much, Ricardo, and everybody. I do appreciate the feedback. Super awesome. Okay, so whenever we have on our learning management system, when we have a new machine, we're going to provide documentation. Everything is well documented. And we're going to step through. We're going to explain the tree. We're going to explain the method, the support vector machine, the artificial neural net. It's a lot of fun, right? We want to make this a real educational tool. And then we'll go ahead and get started. Now, I'm going to just kind of scroll through this because we don't have time to go through all the details, but we would go ahead and introduce lots of ideas around data, data analytics, checking the data, test train splits, and so forth. I'm going to need to, in fact, run this code, though. Okay, so let me go ahead and run this. We would also spend time talking about Jupyter notebooks. How do we design our workflows, prototype them? How do we test them and check them? and all of that. Exactly. Okay, so what we'll do now is we'll go ahead and we'll load a data set up. We have this specific workflow available in the learning management system if anybody wants to check it out. I do have a bunch of workflows also available on GitHub. Thank you very much for asking that question. And I'm Geostats Guy on GitHub. Okay, so now let's go ahead, we'll do a train test split of the data. We don't have time to talk too much about these details, but we will go ahead and we will build a decision tree. Okay, so what we have here is we have porosity and we have brittleness, and we're trying to predict production. This should look similar. You should have a pretty strong case of deja vu right now, because this is exactly the data set I was showing on the lecture notes with a better color map. Actually, I like this color bar better. This is my training data. This is my withheld testing data right here. Now, just a little bit of a note or piece of advice, you'd want to look through the training data and the testing data and make sure that it's a fair train test. In other words, I would be concerned if I was making predictions in testing that were outliers relative to the training, and I would be concerned that would be too hard. And I would be concerned if all of my testing data were right on top of the training data. That's too easy. We want to make sure we're being fair about this. Okay, so that's training and testing data. We're going to go ahead and build a decision tree. Now, you know, Todd, that's an excellent question about what would be a fair or good split in training and testing data. There have been meta studies conducted across a large number of examples of machine learning. Commonly, you'll see between 20 and 30% withheld for testing. Now, to explain the logic, we can all understand that if you use too many data for testing, you're going to sacrifice the goodness or the coverage in training. And so you result in a worse model. And if you use too few data in testing, then you're not going to adequately test the model. You have a great model, but you don't really know it's great. Okay, my recommendation is often to go away from random test train. I do demonstrate random test train here, but to really try to engineer it and make sure that the testing data covers the entire space or the difficulty of the estimates you want to make in reality or real use of the model. Todd, does that help you out? You like that? Okay. So let's go ahead and build a tree model. I want to point, thank you very much for that response, Todd. Oh, let me just show you something really cool about using scikit-learn. And we have an entire lecture where we go into scikit-learn. You'll notice that your first step is to take and instantiate the object, the machine, my tree. At that point, you'll set the hyperparameters. For a decision tree, the maximum number of nodes or regions, as I explained it before, is a very easy way to set the model. Once you've done that, then you will fit the model with the training data. And then you want to check the model by predicting at the testing data locations. Now, I wrote two convenience functions so we can in fact visualize and see what the model looks like. Okay, so let's go ahead. What I'm going to do is let's change the maximum number of nodes to something smaller. So if we have only 4 regions, I can run it and you can immediately identify the fact that we have 1, 2, 3, 4 regions. So we were able to build a tree. If you think about it, that's just a tree with 1, 2 levels of splits, resulting in 4 possible regions at the end. So that's a very small tree. And you can look right here. If you don't believe me, if that seems confusing, well, look at this. These are the estimates from your decision tree. Here's the actual production, 1, 2, 3, 4 stripes or striations. So what's going on here? You only have 4 regions. You're predicting with the constant value in each region. Okay, let's go ahead and we could change. Anybody from the audience want to suggest a number of nodes you'd like to see? We're hyperparameter tuning by hand now. Anybody have a number you'd like to use? If you don't say anything, I'll say 13, my favorite number. I bet, Avi, we have a little bit of a lag, don't we?
I'm good on my end, Michael. Yeah, you're fine.
Because I've noticed that the answers start rolling in.
There you go.
Okay. Now you only see 3 colors, Austin. That's a great question or comment. The reason being is that, well, first of all, let me ask the audience, would it be possible to have a region shaped like that given the hierarchical binary segmentation approach? Could we actually have a region with a corner? And the answer is you can't. This is an artifact of the fact that we have 1, 2, 3, 4 regions, and we just happen to have the estimate between these 2 regions is very close to each other. Okay, let's test that. How could we test it? Let's check what would happen if we had only 3 splits. Okay? Do you see what's happening right there? So we 1, 2, 3 right there. Okay, and let's go back to 2 splits. So that split was made on the 3rd. If we go back, look at that. You see that? We had, these were the regions, and then we did a split right here, and the colors just seemed very similar. Okay, let's go ahead and overtrain this. We could go ahead and put something like about 30 or something like that. Another hyperparameter would be the minimum number of data within each one of the regions. We could do that too to make sure we have a good estimate of the average. You can see right here, we've done hyperparameter tuning by hand, and the result is we can see that we now have a much better fit. It's getting much more accurate. Okay, so let me just comment on the fact that we could, of course, run this many times, and we could do that in order to check and see our performance over many models. And that's what you'll do in hyperparameter tuning. Here's the mean squared error in this case, not the residual sum of squares, but just the average squared error. And you can see the performance over multiple number of regions, or what we call terminal nodes and decision trees. And you can see that we do quite well. This example is very simple. It does not have a lot of noise in it. It's a smooth shape. And so what we see is that we kind of maximize here, and it kind of creeps up a little bit, but we don't see a problem with overfit with this example. Okay, so that's it. So we have an example. Let's go ahead and let's extend this concept with the remaining time to ensemble tree-based methods. Okay. Let's go ahead and I'll just switch my displays. Okay. Let's talk about ensemble learning right here. Okay. Ensemble methods. So what's very interesting, if we look at the actual error in our models in testing, and we were to do a really cool calculation. This is the expected test mean squared error. These are the truth values at testing locations. These are the predictions at testing locations. And we take the expectation of the square. If we do that and we take that quadratic and expand it, we can simplify it to 3 terms of error. And this is demonstrated in the book, James and all, if you want the derivation. So we have model variance, model bias, and irreducible error. Now, it turns out that if we increase model complexity, that we're going to decrease model bias. Think about it. A linear regression model could have a lot of error due to the fact it's too simple. It's an approximation that's unable to match the true data. That's model bias, okay? Model being too simple. Model variance is the model's too sensitive to the data. Okay, now let's think about that. A first order model, like a linear regression model, it will just move around a little bit if you change the training data. A 7th order polynomial like we saw, if you change the training data, it's going to whip around like crazy. It's going to go all over the place. A very simple model has low model variance. A complicated model has a high degree of model variance. And irreducible error is error due to the fact that we have limitations with the data. We don't have enough data. We don't have enough samples. We didn't sample the full range of the phenomenon. Now, it turns out that a good way to reduce error would be to, or variance, would be to take averaging. In fact, averaging is a very efficient methodology to reduce variance. If you go back to the concept of standard error, the variance of an average is equal to the original sample variance divided by the number of samples. That is standard error in the mean. Okay, so we know that from theory. So we can go ahead and do an averaging of our estimators. We will get a much more accurate estimate. Now this requires multiple prediction models. The way we can accomplish that is we're going to need to work with multiple data sets. Now this is crazy because we only have one data set, so we're going to have to do something. Anybody here ever heard of the BOOTSTRAP before? Anybody here ever BOOTSTRAP? Use BOOTSTRAP? The BOOTSTRAP method. We can assess the uncertainty in a sample statistic by repeated sampling. Okay, I hear some yes and no's. Good to introduce. For those of you who have never used the BOOTSTRAP before, today is truly a great day. And it'll be a good reminder for everybody else. by repeated random sampling with replacement. So we can get uncertainty in a sample statistic. In fact, we can get uncertainty in the entire data distribution by repeated sampling with replacement. Okay, let me show you what that looks like. We take the sample data, that's our original data, just 10 samples, very, very simple. We build the CDF. We do 10 Monte Carlo simulations. That's 10 random draws with replacement from the data. We get a new distribution. We calculate the statistic of interest, could be the entire distribution. We get the mean in this case, that's a realization of the mean, number one. We put it right here. Then what we do is we repeat. Would you all agree that if I repeat the bootstrap process, I would get a different distribution? 10 random samples would look different. Isn't that cool? We get another realization of the data, get another realization of the average. Okay, and we repeat. And if we do that enough times, we get an uncertainty in the sample statistic, the mean. Now, but every one of these was a realization of the data. We could use that in machine learning. Let's do that. Okay, so how are we going to do that? We're going to apply the statistical bootstrap to obtain multiple realizations of the data. Each one of these are realizations now. We build a prediction model for every realization. Okay, we'll do this multiple times, and then we can pool the predictions. We get a prediction for every one of those realizations. We're going to pool that. This is super cool. The way we can pool it in regression, we'll take the average. Now, I apologize. I should have put a 1 divided by big B here. I missed that, but it's just an average of all of the estimates. Or if it's classification, you can take a majority rule approach. Isn't this cool? This will totally fight against model variance and give us a much more stable, much better behaved model. Okay, let's introduce the idea of tree bagging, and we'll run out of time about there. We'll do a little poll and we'll be done for today. I won't be able to jump into all the details around random forest because I want to show you guys examples of this. Tree bagging. What we're going to do is we'll build an ensemble of decision trees with multiple bootstrap realizations of the data. The ensemble approach reduces model variance as expected. Now what's really cool is overfit gets dealt with pretty well. We can grow the trees to be too complicated. And in fact, that averaging process will help us fight against overfit. Now this is something really important. It turns out every time you do bootstrap, resampling from the data, statistically speaking, about 1/3 of the data will not be used. Think about that. What does that mean? It means that you're going to be drawing other data values more than once, twice or 3 times and so forth. And as a result of that, about 1/3 in expectation will not be used. Every time that happens, we treat that data as out of bag samples right here. Now, this is very cool because every time we train a tree, we can then make a prediction at the out of bag samples because we didn't use it to build the model. Now we can build the model and cross-validate the model, training and testing all at once. So with tree bagging, we don't have to split the data up. Now it does have the assumption of random selection from bootstrap, and so let's be careful about that, but we'll recognize that. We want the trees to be decorrelated, maximize their ability to reduce the variance. This is the random forest approach, and I'll comment on that. Okay, so what's it going to look like? We're going to build a decision tree from a bootstrap realization of the data, build a decision tree from the bootstrap realization of the data. Do you get the pattern here? Do it here, 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 here. I did 6 of those, and then I averaged them together. So this is porosity brittleness, making a prediction of production, MCFPDs, and look at that. What's the observation here? Can you see this? This is an average at every single location of all of these models. First observation, you notice how the discrete step-like nature of the decision tree is dampened. If you do many, many trees, it will smooth the model out. We don't have that step behavior, okay? Now, what's the impact of this methodology? Well, first of all, if you go 1 tree, 3 trees, 5 trees, 10, 15, and 30 trees, you see how they're getting smoother. So that discontinuous behavior of the estimator is being smoothed out. And I think you can see that perfectly well now. Now, if you didn't really kind of see it as well, Look at the actual cross-validation results. Estimations, the actual values, you can totally see that, right? You're starting to smooth out. You don't have the striations anymore. There's something very cool here. You can also observe the reduction in model variance with averaging more trees. Okay, we know this intuitively, that if you just build one tree, one tree, one tree, and you compare them to each other, this is really like decision trees. And if you bootstrap, you can go ahead and see the difference. Can you see the differences between these models? They're shifting and changing pretty dramatically with their estimates. Just look across here. By the time you get to 10 trees, 30 trees, 100 trees, it starts to stabilize. That is a visualization of reduction in model variance, my friends, and that's super powerful. Okay, now Mustafa had a question here. Are we using Markov chains? How do we decide that X iterations are optimum? Now, this is a very good question. I think you're referring to the number of bootstrap realizations. And here's the trick. And this is, I'm gonna keep it kind of, not too super technical. It really is use enough. If we have enough bootstrap realizations, we'll get good performance. It will. Now, if we use too few, you don't get the benefit in the model variance reduction. Now, you can check that, and I'll show examples here right away where I may not have time to get into them, but we can show examples where you can see that the performance of the model actually reaches asymptotically good performance, and it does not kind of go back down as you increase the number of bootstrap realizations. Okay, all right. What I want to do now is I can't do all of this and not check your knowledge. I really feel, I would feel bad if we went through all of this and there was no chance to ask you some questions. Okay, so let me go ahead. Okay, remember we talked about machine learning. Remember we talked about the various aspects of machine learning. Let's just see what machine learning, select the aspects of machine learning, a toolkit of algorithms, training with data, improve their performance through training without being explicitly programmed for that problem, a general approach. Okay, I've only got a couple of responses so far. We're going up to 6 responses, 10, I'll wait till I get almost to about 20. Good, I'm seeing a lot of people getting this. This is very good. What are the aspects of machine learning? Okay, 18, and I will end the polling, and I'll show the result. Okay, so everyone's correct if you said any one of those, but machine learning is all of them. Toolkit, train with the data, improve performance through training, and it can be generalized. Okay, let me go ahead. I'll just ask a couple more specifically on decision trees. Okay. And, oh, this is a good one. Okay, can you guys see the question now? A decision tree. Decision trees segment the predictor feature space to make predictions. What is the prediction calculation for a decision tree? The average of all estimates from the decision tree, the average of the training data within a region of the prediction case, the average of the testing data within a region for the prediction case. How does a decision tree make a prediction? I think this is really important. This is nuts and bolts. Let's make sure we understood what we just saw. I've got 5 responses now. I'll give you guys a little bit more time. Let's prove our knowledge. Is it taking the average of the training data within a region? Is it taking an average of the testing data within a region? Or is it taking the average of the estimates from multiple decision trees? Okay, I've got 14 responses now. I'll end it in 3, 2, 1, end polling and share the result. Okay, so good job, folks. Remember, and this is critical, I like to ask multiple choice questions that illustrate an important concept. And the concept here is this: we use the training data, okay? When we're making predictions, even though we use the testing data to tune the hyperparameters, the model is still based on the training data. It's the average of the training data in the regions, not the testing data. And remember, the averages of multiple estimators, that was the ensemble approach, like tree bagging and random forest. Okay, let me go ahead. I'm going to ask one more question right here. Let me ask. Oh, this is a good question. Okay. Well, we didn't cover all of them. Okay, but let's see if you guys can extrapolate to this. Okay, decision tree. Which one of these are hyperparameters for a decision tree? The minimum number of samples per leaf or region, the maximum depth of the tree, the number of layers you can have. Remember, a decision and then decision and decision. It's a tree, so you have multiple layers. The maximum leaf nodes, number of regions, or all of the above. Okay, I've got 7 responses right now. You guys, the answers are flying in. Which one of these actually control the complexity or flexibility of a decision tree? Okay, I've got 16, 17 responses. I will end it in 3, 2, 1. Okay, let's go ahead and show this. Share the results. Good job, guys. So all of these are hyperparameters. Remember, every time you see a potential hyperparameter or parameter, ask yourself, would it control the complexity or degree of fit of the machine? If I was to change the minimum number of samples per leaf, that would be an upper threshold on the number of terminal nodes or regions I could have. It would stop the splitting. If I had max depth of the tree, that would also control it. And finally, the max leaf nodes is the one that we used. Okay, good. Awesome, you all. So what I'm going to do is I will stop there. Avi or Kunal, did you all have anything else you want to say?
Hey, Michael, that was great. Great introduction for decision trees, random forest. I just wanted to say too, if any of you enjoyed this topic and want to see more, Michael does a great longer lecture for 4 days. I know I showed it in the beginning, so would love to have all of you join us there. We have 25% off today as well, so please feel free to join Michael and us for the longer courses as well. So appreciate the time, Michael, today.
Awesome. Hey, thank you very much, everybody, for attending. If anybody has any final questions to ask or anything, I would be happy to entertain questions. Always discussion and interactivity is welcome. That's how we learn best. Everybody else, stay safe, and thank you for joining in. Really appreciate it. Avi, thanks for the great help today. Hey, Mohammed, thank you for joining in. Appreciate it. Mustafa, hey, thanks a lot, guys, for the interactivity. I appreciate you guys jumping in with questions and comments. Makes it so much more fun. Leonardo, yes. Santosh, thank you very much for joining in. Appreciate that. Thank you, Johannes. I appreciate the interactivity. Great questions. Hey, see you, David. Appreciate it. I hope it was accessible and understandable. That's for sure. We go for that. Thank you, Kevin, for joining. Appreciate it. Do you think that snake is still in my backyard, Avi? Hey, thank you, Kevin. Appreciate it.
I hope for your sake and dog's sake that it's not there.
I know. It's a coral snake.
Strange
coral
times.
snake. And my concern is, I know to stay away from a coral, and they're pretty docile. But the dog, I think the dog will just go after it. And
yeah,
I'm
especially out of curiosity.
Yeah, and I don't think the dog would get bit because it is a small coral snake. Hey, Achilles, appreciate it. Thank you for joining in. But I'm also worried about the dog getting acclimated to attacking a snake, or I don't know if it'll try to eat the snake too, right? Like if that would be a problem perhaps, right?
I know.
Okay, Mustafa had a question here. Can random forest be converted into loops for decision analysis? That's very, very interesting. If you think about it, there's already a loop within random forest. Okay, so I'll just make a couple of comments around that with the multiple ensemble estimation. At the same time, I often see people use random forest within a recursive feature elimination approach. And that can be very, very cool, where you build many different models with different features and you see the performance. And then from that, you can assess, like a tournament manner, you assess which are the most important features. I think often knowing the most important features can definitely impact the way we make decisions. That can be very powerful. Plus, it can improve the clarity of the problem. The high dimensional problems. The curse of dimensionality is not just visualization. There's all kinds of issues of high dimensional data sets. So definitely can assist us. Yeah, I like it. Now, when you get into real decision making in the face of uncertainty, you can start imagining the model being constructed as a large Monte Carlo simulation loop with decisions. Boy, then you're getting into some game theory. Now you're starting to simulate the real game, and it's pretty powerful stuff. Yeah. No, thank you, Mustafa. That's an excellent question. If you were in one of my courses, I'd be like, yes. That's great, because that's getting us to think about the applications of these tools. Can be very powerful. Yeah. You know, Kelvin, this is a very good question. How do we determine the hyperparameters to tune? So it's a good point, because they're not independent of each other. That's for sure. Like if we're in the case of a decision tree and we have minimum number of data per node or region, and we have the maximum number of regions, and then we could have the minimum reduction in residual sum of squares. There's a bunch of different hyperparameters you can tune. My tendency is to, in that case, work with the one most understandable hyperparameter if I can. And in decision trees, I think that's fair. I think the number of nodes is a perfectly good way to constrain a decision tree. The reason being, it's a very simple linear incremental behavior, right? Like you just explicitly state how many nodes. If you do a minimum RSS reduction and so forth, you'll find yourself in a situation where you'll have kind of jumps and starts, right? It may not behave as you expect. One cautionary note though is make sure you don't go so far with the maximum number of nodes that you get nodes that have too few data. And so you might actually want to leave a minimum number of nodes, not tune it, but leave it in there so you don't end up with fitting noise locally. Okay, so that, but then I would still focus on the maximum number of nodes. Okay. Now, of course, if we get into more advanced machine learning, like convolutional neural nets, and you're starting to talk about dropouts and training rates and so forth, yeah, now you got to think about, how are you going to tune those, and you probably have to consider them all at the same time. And I've had a student who's been doing some really interesting stuff around optimizing tuning like that. It becomes a sampling problem for sure. It gets to be large, the space. Good. Thank you very much, Kelvin. Any other questions? It's been an action-packed day today. AAPG, chairing, and I think I'm going straight into meetings after this.
You're a busy man, my friend.
I know.
I think we have a hand.
Pardon me?
I think we have a hand up with Kevin as well. Kevin, did you have a question?
Oh, yeah,
we should let him talk. Oh, there we go. There you go, Kevin. I put your mic on.
Yeah, unmute. Let's talk. Yeah, gradient boosting. There's a question here about gradient boosting. And, just to make a comment, they're both around the idea of an ensemble approach. The gradient boosting is really interesting because the fact that you learn slowly and you treat it like a stochastic gradient descent. The bootstrap approach actually introduces stochasticity into the approach. It's really, really interesting. I would agree. Gradient boosting approaches definitely are competitive with the, very powerful methodologies of machine learning. There's many categories of problems where they perform very well. The one thing is that the incremental knowledge you have to have as far as stochastic optimization or stochastic gradient descent approaches for optimization, it does pose it as an optimization problem. So there's a little bit more prerequisites to learn to do it well, for sure. Okay. No, thank you very much, Gregory. I appreciate the question. Good. Avi, I better jump out because I am pretty sure.
Michael, absolutely. Yes, for sure. Thank you so much.
Hey, thank you. Everyone stay safe.
Talk soon.
Okay. Bye.